Good morning. Really cool to have all of you here, and happy Friday. We're going to continue on with an example we left with on Wednesday, and I kind of rushed through it, so I'm sorry about that. So we're going to go a little slower here. We're looking at some of the techniques that are used to solve these equilibrium concentration problems. And this is one where you have a clear NO2 the brown NO2 and a colorless N2O4. And they have an equilibrium constant of 0.0059. Now on Wednesday, we talked about how there's a difference when you have a K value that's less than 1 or a K value that's greater than 1. So knowing this is the value of K, would you expect more reactant N2O4 or more product NO2? Reactant, that's right. K less than 1 means in equilibrium studies that you're going to have more reactant, in this case N2O4, than you will have product NO2. There is a temperature dependence, and we'll talk a little bit more about that, I think, today. But anyway, at this temperature, this is the equilibrium expression. We would expect to have more reactant because K is less than 1. If K was greater than 1, we would expect to have more product. So anyway, in this problem, we're starting with 0.50 moles per liter N2O4. And once equilibrium is established, we want to know what the equilibrium concentrations are. And again, the actual value of K tells us that we should end up with more N2O4 at equilibrium than we have NO2. So like on the other problems, what we'll do is we'll set up an ice table. And all we really know initially here is that in this problem, we start supposedly with pure N2O4, and we don't have any NO2. And then, like we've seen this week, the stoichiometry of the reactants and the products will help us in this change part right here. And what I mean by that is that one N2O4 is breaking down to create two NO2s. So you can use X there to represent the amount because we don't know what the amount is. And you can see how there's like a 1 to 2 ratio. And that comes again from 1 mole of N2O4 breaking down for every 2 moles of NO2 that are formed. And you can also tell that there's a negative there and a positive there. And in an equilibrium setting, you must have both products and reactants, all right? So you have to make some NO2 to make it actually in equilibrium, and it will come at the expense of the N2O4. So at equilibrium right now, all we can really say is that N2O4 is going to equal 0.50 minus X, and the NO2 will equal 2X. Any questions on this part here? Cool. So what we did then next is we placed it into the equilibrium constant expression. And again, because of the 2 right there, we're going to square the NO2 concentration. So because NO2 at equilibrium was 2x, we need to square that whole quantity right there, 2x squared. And in the bottom part, N2O4 was equal to 0.50 minus x, and all of that equals the equilibrium constant K. Now, if you look at this problem, it's kind of cool because there's only one variable, x, all right? So we can solve this expression for x. And to figure out the equilibrium concentrations then, 2 times x will be the NO2, and 0.50 minus x will be the N2O4. But of course, we have to solve for x. So when you rearrange this beast, 2x quantity squared is 4x squared. And we'll multiply both sides by 0.50 minus x. That gets this out of the bottom and puts it up here next to the equilibrium constant. And from there, I'll take the K and multiply it by both of those terms. I end up with these parts right here. And then finally, I'm placing it into what's going to be a quadratic formula expression. And I'm sure quadratic formulas are something you do for fun on the weekends. Don't throw tomatoes, please. Anyway, a quadratic formula is fairly common in algebra. And what people usually do is they set it up with something that looks like ax squared plus bx plus c equals 0. And if you have those terms, that's when you can start plugging into the quadratic, which we'll show on the next slide. So again, you put all of your terms like on one side, you let them equal to 0, and it's the actual numbers here that come out. And again, just to be clear, like C is negative 0.0029, all right? It's always ax squared plus bx plus c equals 0, equals that, and you're good to go. Now, with these terms, with these a, b, and c terms, you can plug it into the quadratic. This is the quadratic formula, minus b plus or minus square root b squared minus 4ac, and all of that over 2a. Now again, notice the plus or minus. You're going to end up with two solutions for these problems, and we'll talk about how to predict what the correct solution is. So in this problem, you want to plug in that a, b, and c term. So you can see here the opposite of b, minus 0.0059, plus or minus, and then the square root of the b squared minus 4ac. Again, because c is negative, that times the negative 4 will end up being positive. And at the end, then, going through some math, and if you haven't done this for a while, it's cool just to make sure you're up to speed with it. You come up with this thing right here. It's the negative amount plus or minus 0.027. Now, if you take the negative 0.027 and you add it to a negative 0.00074, you're going to end up with a negative number, negative 0.028. The good thing about chemistry is that mass, which is related to moles, which is related to atoms too, but more importantly here it's related to molarity. Those things can't be negative, all right? Only in kind of cool physics kind of applications sometimes, I'm looking at Travis here, only in some kind of cool physics things, maybe you can play with the idea of negative mass, and that's kind of fun to think about. However, I'm already excited enough by Shazam this weekend, so don't get me started, prop that back on. So what it comes down to, don't use negative numbers here, all right? The mass numbers, the moles, the molarities, they all have to be positive. You can't have a negative value for the mass. So if you get an x which is negative, automatically disqualify it and use the other one. So in this one, we're going to use an x of 0.026. And this is the magic x that I talked about earlier, because this x will allow us to find out the N2O4, 0.50 minus this number, we're going to have 0.47 moles per liter N2O4. And then 2 times x will be the NO2, so 2 times this number, 0.052. And at this point, because obviously the math is a little weird, you can go back and check yourself and see if the answers make sense based on your K. So K was a number less than 1, all right? And K is less than 1, mean you should have more reactant than product. And if you look at these numbers, 0.47 is definitely a lot bigger than 0.052. So that part kind of falls into line. So this is an answer then that makes sense. Now, one more advertisement. The calculators, like the T89s and stuff with the solve buttons, goodness, those are really cool. And that's one way to get around using the quadratic formula. So if you have a calculator with the solve button and you know how to use it, the calculator will do the heavy lifting for you. You'll end up with these two x values, pick the positive one, not the negative one to do it. And that's a cool way too. Once in a while, we will have a quadratic in this class to solve. All right, there's some ways to get around it. We'll talk about those in the next chapter. But I am introducing it because it is a skill set that you should at least be somewhat familiar with, so that if you have to do it, you can do it. Any questions on any of this stuff? All right. The last big thing we're going to talk about is probably the thing we'll talk about even more than equilibrium in this class, and it's a really fascinating idea. There was a guy named Le Chatelier, and that's how I've always heard said it, and if you can say it differently, that's fine, but I'm going to say Le Chatelier. Anyway, it's a long story I've had conversations with people about. But anyway, Le Chatelier was actually an engineer, a miner. He was in mines. And he noticed that sometimes changing things would have a result, an effect. It's like every action has a reaction in a nutshell. So he formalized this and stuff into what's called Le Chatelier's principle. It works really well for describing changes to equilibrium, but there's a lot more you can do with it than even he anticipated. There are lots of things that affect the equilibrium, all right? You can change reactant and product concentrations. You can change the temperature. Sometimes you can even change like the pressure of things. And all of those, you can make a reasonable prediction using Le Chatelier's principle. Now, here's the formal definition of Le Chatelier's principle. And if it sounds like wah, 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 that means it's just don't tune me off a little bit. However, if a system at equilibrium is disturbed, the system tends to shift its equilibrium to counter the effect of the disturbance. And I know that's probably not as clear as mud. So imagine right now that Hunter, who is so benign and so cool, comes up, oh, Russell, I'm really mad. And he takes a swing at me. Okay, he would never do this, but let's say he did. This is all, acting, you're an actor. Anyway, he takes a swing at me. All right, probably I won't just stand there. Probably I'll try to do this kind of thing, like get away from it. And believe it or not, this incredibly cheesy explanation is an example of Le Chatelier's. If someone comes up and they're like, in your face, you kind of go back like that. That's actually a way that you're reacting to a stress. Now, a stress, in this case, is obviously avert and stuff like that, quite obvious. In equilibrium, a stress can be an effect of adding extra reactant. What are we going to do with all this reactant? It can be in the effect of taking away the product. Oh my gosh, my product's gone, I have to make more. A shift in the equilibrium is like a stress on the system, all right? I apologize for using violent imagery. That's really not how I roll. However, I wanted to make it quite clear kind of what's happening here, man. So think about these cheesy things while we go through this. Now, first type of change we're going to look at is what happens when the temperature changes. And the temperature change, we can use Le Chatelier to figure out what it is, but there's a little bit of a difference. Most of what we talk about with Le Chatelier's principle doesn't actually affect the value of K. It affects the position, and we'll come back to that later. So if you have a temperature effect, you raise the temperature or you lower the temperature, you're actually going to change the value of K here. Here's an example. It's Friday. You decide to go home and have a celebratory root beer, and you open up the thing. Hopefully you hear some fizzing and stuff kind of going on. In a soft drink can, you can write a type of an equilibrium, all right? There's like a gas, all right? The carbon dioxide is usually the source of carbonation. It reacts with the water. It becomes dissolved carbon dioxide, like in the solution. And actually this reaction has been studied, and it's found to be exothermic. Now, in an exothermic reaction, heat is created by the reaction itself. So if you could actually feel it, it would feel warm because heat is being generated. An endothermic reaction would have heat needed to proceed. Heat would be a reactant in that case. So one thing I want to point out here too is that if you see heat as a product, that's one way of saying it's exothermic. And if you see heat as a reactant, that's another way to say that it's endothermic. Now, let's have a little thought process here and say that before we open our root beer, we want to put it in the refrigerator. All right? So what we're going to do is we're going to put it in the refrigerator, and the refrigerator is cold. We're lowering the temperature. Le Chatelier's principle helps us to figure out how this soft drink is going to react. If you get cold, you go outside, you go snowboarding or whatever, do you take off your coat or do you put your coat on? Bear with me. Yeah, you put it on. All right. Sorry, juvenile. Anyway, prop that back on. Really, there's something relevant here. If you go outside and you're cold, you put something on to keep yourself warm. All right. The soft drink is going to do the same thing. If you start lowering the temperature, putting your can in the refrigerator, all right, the reaction, you can literally think about it as getting cold. And because this reaction is exothermic, it's going to try and make itself warmer. But a soft drink doesn't have a coat or a sweater to put on. It can only create heat. And the exothermic, endothermic part is really important here. So in this reaction, if you lower the temperature, the reaction is going to try and warm itself up. This really weird way of thinking about a reaction is totally effective, and it doesn't seem reasonable on one level, but it does work. Now, if the reaction's going to make more heat, are you going to see more product, do you think, or less product? More product, that's right. Heat is on the product side. The reaction is cold. It's going to try and move to the side to warm itself up. You should see more product. In this reaction, you can write an equilibrium constant. This is called a mixed equilibrium constant. Don't be too worried about that. We have a moles per liter CO2 because it's a solution, and we have a pressure of CO2 gas. So we would expect in this one to see an increase in the value of K. As the reaction shifts to the product side, more of the CO2 will dissolve. This is CO2 above the water, or your root beer, whatever, it's free, all right? As the reaction makes more heat, what it also means is that the CO2 is going to become more soluble. All right? So in this case, if you cool your pot can down, more of that CO2 is going to get in the water. You should have more dissolved CO2. But now, let's take our cold can out of the soft drink, and let's warm it up a little bit. We're going to increase the heat. Now the reaction is no longer getting colder, it's getting warmer, all right? And if you were outside, you would take a coat or sweater off or something like that. And again, the reaction can't do that. But if you're increasing the heat, what's going to happen is it's going to try and not have as much heat. It's going to try and use it up. So in this context then, the equilibrium is going to shift to the left. And what this means for this equilibrium, you're going to have less dissolved CO2 and more free CO2. So your can of pop is going to make that sound. That's the free CO2, all right? And as it warms up, more and more of the CO2 starts coming in. So in this discussion we've had, which is a little weird, the stress, all right, that I've been talking about is either decreasing the temperature or increasing the temperature. And what's happening here is that it's trying to get away from the stress. So we lowered the temperature, we made it colder, the reaction's going to try and shift to the side with the heat. On the other hand, we increase the temperature. Now the reaction's getting too hot. It's going to try and get away from the heat. So notice here I'm thinking about the position of the heat and what the effect is on it. Any questions on this? Okay. Let's go back to my NO2 N2O4 example. Now earlier we saw that at 298 Kelvin, the equilibrium constant was 0.0059. Reactant favored, all right, and this is about room temperature. Notice here that at water's freezing point, 273, the equilibrium constant, 0.00077, all right? So is this reaction, as you lower the temperature, is this reaction becoming more product favored or more reactant favored based on those numbers? Reactant favored. The K is getting smaller. It's going more towards the reactant as you lower the temperature. Conversely, if you increase the temperature, you'd be going from the colder to the warmer temperature. You can see K would be getting bigger that way. You'd be going more towards the product side. So when people study this, this is an endothermic reaction. It actually takes energy to break the N2O4s apart and make NO2. So in this reaction, we have a positive delta H. That's another way of saying that you have an endothermic reaction. Heat is a reactant. As you raise the temperature, as you go from the blue to the green temperature, K is getting bigger. That's because raising the temperature makes the reaction try and cool itself down. It's trying to get away from the heat side. It's going to make more product, less reactant. Still reactant favored overall, but not as reactant favored as it was before. Conversely, you cool it down, green temperature to blue temperature, all right? Now the reaction's getting cold. It's going to try and shift to the side where the heat's being generated, which in this case is the reactant side. It's going to be becoming more reactant favored as this goes on.
In a sealed flask, we have a mixture of dinitrogen tetroxide, a colorless gas, with the brown gas, nitrogen dioxide. When we heat the flask, however, the dinitrogen tetroxide decomposes into nitrogen dioxide, creating more of the brown gas until equilibrium is reached for the higher temperature.
On Wednesday, I told you my cheesy story, how I dumped a flask in an acid bath way too early, and this big rush of brown gas went up. Well, as you can see now in this weird example, this interaction is endothermic, and there was definitely lots of temperature. It was very warm in what I did. The gas I saw was incredibly brown, very, very dark brown. Really kind of freaked me out, as you can probably tell in my subconscious level. But anyway, very lots of NO2 being created. As you increase the temperature, and there was a lot of energy created there, it's going to shift to the brown side. You see the gas gets much, much more brown. On the other hand, you freeze it down, the reaction becomes almost colorless, all right? As the NO2 concentration, which is the brown, gets lowered, you end up making more of the N2O4, which is colorless, just like the gas that you're looking at me through right now, which is oxygen, nitrogen, argon, water. Those are all colorless. You can really begin to tell sometimes how these things work out. So here's a reaction. Chlorine and fluorine make chlorine trifluoride, all right? And notice here how we have heat as a product, all right? If heat is a product, that tells you a couple of things. First of all, if heat's a product, it says it's exothermic. Heat is being generated. Also, the sign of delta H here will actually be negative. Delta H, which is the sign for enthalpy, if you remember from Chem 221 or so. Delta H is positive when it's endothermic, like on the last example. This one would have a delta H, which is negative. But anyway, what we're doing here is we're going to raise the temperature on this reaction. And the question is, what happens? Does nothing happen? Does it shift to the left reactant side? Does it shift to the right to the product side? Raising the temperature is like adding a stress of extra heat, all right? So all of a sudden your reaction is like really hot. Ah, man, it's so hot in here, all right? And reactions will my apologies for all my bad theatrics. I see T. Growing what he's thinking. All right, Prof, not really on this time. Sorry, I'll try not to be less. My caffeine was extra good this morning. Anyway, raising temperature. So you're adding energy, you're adding heat. The reaction's trying to get away from the heat, so it's going to try and cool itself down. And the only way it can do that is by moving from the heat side to the non-heat side. That's going to be a shift to the left. So if you raise the temperature on this reaction, you should end up making more chlorine and more fluorine. Let's say that your boss wants you to make chlorine trifluoride. Do you think that in a relative sense anyway, you would want to have higher temperatures or lower temperatures?
Lower
Lower, right on. Making chlorine trifluoride is not helped by having higher temperatures, all right? Higher temperatures will make this reaction shift to the left. So probably you'd want to do this reaction at a relatively lower temperature. And that number, I don't know what that would be, but we would predict it would be lower maybe than we might expect. Maria, you had a question there.
Yeah, can we just look at it as if the heat's on the right side and the shift's left, if it's on the left side and the shift's right?
Yeah, that's absolutely, that's totally cool. It's going to shift, if you're adding, it shifts away, and if you're removing, which we'll see in a little bit, then you shift towards that side. That's kind of the punchline of Chatelier principle I'm dealing with. Yeah, perfect, Maria. Absolutely. Other questions? Yeah.
So it's just heat, right? We don't worry about pressure on the same gas.
Correct, that's right. In this one, we'll assume that the pressure is about the same. This would absolutely, though, be a reaction which is sensitive to pressure. We'll talk about that in a little bit. Good. DeGraw also is seeing the future. Other question? You already told me about the 9 Fridays, man. So you are definitely seeing the future today. I'm just letting you know. Oh, goodness. Anyway, other questions? Okay. Pressure and volume, definitely important. Now, if you have a gas, all right, we saw in Chem 222, PV equals nRT, all that kind of stuff, that definitely pressure and volume can affect gases. So this little conversation right here only applies to systems where you have a gas. If you have solutions and solids, there wouldn't be any appreciable effect here. Solutions and solids, and liquids for that matter, are generally inert to changes to volume and pressure. How these things usually work is you'll have a flask with a certain gas in it, and it's not too hard to put what's called a cannula in here and transfer the contents from flask A to flask B or something like that. And your new flask might have larger volume or smaller volume. You can actually predict how this is going to work out. If you go to, if you change to a larger volume, all right, and as volume gets bigger, your pressure goes down. Pressure and volume are inversely related, as we saw in Chem 222. You're going to go to this side with more molecules. And also, if you have a flask, a new flask with a smaller volume, you're going to have a higher pressure. You're going to go to this side with fewer molecules. Now, in this reaction, again here, N2O4 going to NO2, we have 1 mole of N2O4 on the right and 2 moles of NO2 on, 1 mole on the left and 2 moles on the right, and these are all gases. If you pressurize the system, it's kind of like forcing the 2 molecules together to make 1 molecule right there. So when I say here higher pressure, smaller volume, that means in this reaction you would have a shift to the N2O4 because you have just 1 mole there, and 1 mole is about 22.4 liters at STP and all that kind of stuff. Fewer molecules here if you have a higher pressure. On the other hand, if you have a larger volume flask, it's like more breathing room, all right? The molecules can kind of spread out. In this case, then, you would think it would go to this side with more molecules. So it would go to the 2NO2, where you have 2 moles of gas relative to 1 mole of gas. If you look around right now at the class, all right, you guys are pretty well spread out. All right, there's definitely some collections of people sitting next to each other, but a lot of people are sitting separate, which is fine. If I move this class from 1303 to 2501, where we have recitation, where I talked about the class this week, it's a lot smaller, all right? So that would force a lot of you to sit next to someone or something like that, right? On the other hand, if I took this same amount of people and moved us to the main theater, theater stage, which is just a massive room, man, you guys could spread out all over. I couldn't even see some of you. You'd be so far away. Some of you would be really close. I use that as an example of how this is working. Now, obviously, you aren't gases, but the principle is the same. If you squish things down, you're going to go to the side with fewer molecules, and if you expand it out, you're going to go to the side with more molecules. Nature abhors a vacuum, sometimes people say. That does kind of work in this context.
A sealed flask contains 3 molecules of nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is in equilibrium. If we then transfer the mixture to a flask with a smaller volume, NO2 molecules convert to N2O4 molecules, resulting in a net decrease in the number of molecules. In this way, the system compensates for the decrease in volume by a decrease in gas pressure.
So you can see then how if you do go to a smaller volume, the individual molecules have a desire to kind of pair up, all right? And if you went the opposite way and went from small volume back to big volume, a lot of those molecules would dissociate again into the individual pieces.
Does the color change if you change the volume?
Absolutely, yeah, totally, that's right. It would definitely change because the N2O4 would be colorless. I would predict this would be less brown and the other one would be more brown. Right on. So let's look at this example again, but now we'll think about what's happening and stuff in terms of equilibrium by decreasing the volume of the flask. Now, if you see this kind of question, first of all, remember it only applies to gases, all right? If you had like a solid here and an aqueous thing here, there would be no effect because solids, liquids, and aqueous things are ignored. But this one obviously is a gas problem, so we're good. So to answer this one, you have 4 moles of reactant gas and you have 2 moles of product gas, all right? So you're decreasing the volume, all right? So what was a big volume is being condensed. And in these kind of cases, more moles will shift to the side with less moles, all right? So in this case, you would see a shift to the right. So if your boss wants you to make chlorine ClF3, I would say, well, yeah, try and keep the temperature relatively low. That'll make the reaction go this way by Charlize Principle. But I would also try to encourage you to use a smaller volume because 4 moles will try to go to 2 moles that way too, which is cool.
So in this case, does the heat matter, or is it just the moles that matter?
Right, there's no heat process here. This is just the moles. That's right. Good, good, good. We're not changing the temperature on this particular problem. We're just thinking about the change of the volume. So like if you had a lot of this you wanted to make, it would be tempting to use a huge flask. But in this context, you might do better using smaller flasks, kind of pushing them together. Good.
So for you to share it, they'll make more.
That's right, that's right.
I was gonna say if it was an endothermic reaction, then
Yeah.
what would happen?
So endothermic reaction, then you'd heat it up, but you'd still keep it, if the reaction is the same, you'd still keep it in a small flask. Yeah, good. Good. You're seeing, though, Jessica, the different perturbations that can happen, so that when someone says, I want you to make fill in the blank, these are the things to think about, like the ways to maximize efficiency and stuff. Good. Good. All right. Catalysts don't change K. They don't change the value of the equilibrium constant. Catalysts, like we saw in Chem 2, the end of Chem 222, they just make you go faster to the products. It lowers that energy of activation, if that means anything. So catalysts are sometimes thrown in here as a way to affect equilibrium. It doesn't really affect equilibrium. It just makes it faster to get there. We saw some stuff with reaction quotients Q, all right? Q is basically a way to see if your reaction is at equilibrium or not. The chances of you using Q with a catalyst, probably not real great, because if you have a good catalyst, it should make your reaction go faster. This is an example of a reaction, the Haber-Fish reaction, which we saw earlier. This reaction makes ammonia, and at 298 Kelvin, supposedly the K 3.5 times 10 to the 8th. So knowing that this is the reaction we're studying, at room temperature, would you expect to have more ammonia or more reactants? Ammonia. K is larger than 1, all right? And anytime your K is larger than 1, more products, less reactants. This is a pretty big K, so it's a really good way to kind of force it over to the product side. There's different catalysts apparently available for this reaction. Some of them are top secret, they're patented, and I, of course, can't break into those kind of things. However, some of the catalysts apparently are some kind of an iron-potassium hydroxide combination. And I'm not quite sure how that works out, honestly, but it's kind of interesting to see. Really cool background on Haberfish that Hunter can tell you more about if you're interested. So what I'd like to do now is talk about what's another really good application of the Chatelier principle to equilibrium. And where I'm going to use an example of a water U-tube. Now, this isn't the cool YouTube with cool cat videos, which definitely pull me in for way more than I need. But this is an example of having, say, lots of moles of reactant on the left and just a few moles of product on the right. And I'm using this Haberfish because this kind of is what I'm trying to show here. 3 plus 1, 4 moles of reactant relative to 2 moles of product. So if you use your imagination a little bit, this is like the 4 moles, and this is like the 2 moles. Now, in a water tube, all right, you pour the water in, and gravity itself is going to make the levels kind of come together. Imagine that this is our equilibrium position here, where we have a lot of product, not as much reactant, but it is steady, all right, it's not moving. I'm going to pretend here, using an idea of a water tube, to try and show you what happens to the equilibrium constant, or the relative positions of products and reactants, when you start removing and adding different chemicals. And it's very analogous to what would happen if we, say, took water out of one side, or if we added water in. Now, just to make sure the thought experiment here is complete, if we add water to this side, the extra mass will push down, and this side will go down a little bit, and this side will go up until they're equal to each other. On the other hand, if we start taking water away, this side now will push more over to this side, so this side would go down, and this side would go up a little bit. Keep this in the back of your mind while we think about this.
When we add water to the tank on the left, the water in the tank on the right moves up, and that on the left moves down. The water moves from left to right, so we say that equilibrium shifts to the right, as it would if we added more reactants to a reversible chemical system.
Just like when we had a reaction and we added heat, the reaction shifted away from the heat as upon adding it. If we add a reactant to this reaction, nitrogen or hydrogen, the effect is the same. The reaction equilibrium will shift to adjust the stress of what you're adding. So in this case, adding water, you can see it kind of moves things that way. This level went down a little bit, and this one went up. Same thing happens over here. You start adding hydrogen gas, for example, the reaction will shift to the product side. You'll see more things done. So going back to what Jessica asked about earlier, if you add something, all right, the reaction will try and get away from what you're adding. So adding nitrogen or hydrogen, it's going to try and get away from what you're adding. It's going to make more NH3. Back to this reaction. Let's say we add chlorine. We're adding a reactant, all right? Adding a reactant, the reaction's going to try and get away from what we add, all right? So in this case, you could probably see it's going to shift to the product side. The additional chlorine is like having a stress. The reaction's going to try and get rid of some of that chlorine by moving to the product side. The ClF3 will end up making more. How will the fluorine concentration be affected as we add chlorine and knowing this answer? Yeah, it's gonna go, the extra chlorine will make the fluorine go down. Chlorine is gonna be high and it's gonna go down while ClF3 is made, but the fluorine, which was at some level before, will be lower after making it. So these are the kind of things that chemists can use Le Chatelier's principle for, like what is the effect of adding a reactant to a reaction, stuff like that. Okay, let's see another one.
Removing water from the left tank causes water to move from the right tank to the left. Equilibrium shifts to the left, as it does in a reversible chemical system when we reduce the quantity of the reactants.
So in this one now, we're removing a reactant. And believe it or not, this is sometimes really helpful. If you have, for example, a solid on the reactant side that's a contaminant, if you filter out the solid, that's one way to remove some of it. And if you're trying to get rid of over here, then it moves to the reactant side. But anyway, the idea is the same. You're like stealing reactants. So in that case, the reaction is going to go, hey, I got to fill that in, man. So it kind of pushes product back to the reactant. It helps you to go from product to the reactant side. So on the last one, we added something and the reaction shifted to the opposite side. Here, we're taking a reactant away. The reaction's going to shift and try and make more reactant for the stuff we stole. So in this reaction, we're removing a reactant, fluorine. All right, so there's like a hole now right here that's like a big gap. Reaction goes, oh, I can't handle that. This reaction is going to shift, try and filling in that part we take away. It should move to the left, to the reactant side. So again, we can use equilibrium sometimes to really affect how much reactants and products we have if you use these kind of theories. Okay.
Adding water to the right tank causes the water of the left tank to rise as water moves from the right tank to the left. Equilibrium in the system shifts to the left, as it would if we added product to a reversible reaction.
Adding product here is like adding reactant. This effect is similar. The reaction is going to try and get away from what you add. Now, in terms of adding reactant, it's shifted to the products. There are times when it's helpful to think about a reaction upon adding a product. The products will break down and make more reactants. So again, the punchline is you add something, the reaction is going to try and get away from it. Here we go again. Adding a product, ClF3, all right? If you add something, the reaction's gonna try and get away from it. Now before we added reactant, which kind of makes intuitive sense, here we're adding a product, that should tend to make the reaction shift to the left side, all right? So if you want to break this down, or if you want to make lots of reactant, adding a product can make that happen.
Removing water from the right tank lowers the water level of the left tank as water moves from left to right to regain an equilibrium. The equilibrium shifts to the right, as it would in a reversible chemical reaction if we subtracted product from the system.
The Germans in World War I really needed ammonia, all right? It was really important. So when they made it, they tried to remove it right away. Removing a product, the reaction tries to shift in the direction of the thing that was removed. It's like you made a gap. So in this case, the water shifts like this way, trying to fill in the part we removed. Taking away a product also shifts to the right. So if you can get that out, it'll then tend to make more of the stuff which you can pull out and stuff from it. Cool. Any questions on that?
So if you keep filtering it, it'll just keep making more.
Yeah. You're seeing the big picture, Tigran. Let's say this was your reaction, and your boss says, we need all the ammonia we can get. Hopefully not for Germany in World War I. But anyway, that's what, okay. Here's some things I would do. I would add as much reactant as you can shove in there, all right? Because adding more reactant shifts to the product side. I would also try really hard to keep taking away the ammonia as it was made, because that would shift to the product side. And finally, I would try and do it in as small volume of container as you can, because 4 moles on the left, 2 moles on the right, small things tend to push things toward the smaller side. These are the ways that chemists think about the world. Woohoo! Don't run away, please. No, I'm just joking. These are just tools and techniques and stuff that sometimes can help you in your reactions. Questions?
Removing water
We
from
don't do that again. Okay, let's go back to this example real fast, and we'll talk about how this can affect things. Now, this is, again, the isobutane to butane equilibrium, all right? K is greater than 1, so that means more product. And the way we've described this reaction, that means you're going to have more isobutane than you're going to have butane. So let's say that we have an equilibrium, and the equilibrium has an isobutane concentration of 1.25 moles per liter and a butane concentration of 0.5 moles per liter. If you take 1.25 and divide it by 0.5, that's going to give you the equilibrium value of K. So before you look at the Nelsons, that is an equilibrium position, all right? More iso, not as much butane. However, we're going to disturb the equilibrium by pushing in a lot of butane, 1.50 moles per liter. That's quite a bit. What we can do now is figure out how the reaction is going to shift. And we can do it both conceptually, in terms of Le Chatelier's, like what's happening. We can also do it mathematically. Now, this graph down here is sometimes something that helps people. This slope of the line here is 2.5, all right? And on the y-axis, we have the isobutane, and on the x-axis, we have the butane. So as long as our concentrations are on that line, the line of 2.50, then we're at equilibrium. But the minute we start disturbing it, then we'll see we're not at equilibrium. And again, all these reactions want to go back to equilibrium. So we'll see how this works here.
Butane and isobutane can interconvert to reach a dynamic equilibrium. The graph shows the equilibrium line. If we add butane to the system, the equilibrium is disturbed, and the butane reacts to form isobutane until the equilibrium is reestablished.
This little dot right here is the 1.25 isobutane and the 0.5 butane. It's these 2 points right here. It's right on that K value of 2.50. This little dot right here represents the disturbed equilibrium. And what I mean by that, 1.50 moles of butane have been added to the system. So 1.5 plus 0.5, you can see now that the new butane concentration is 2.0. And this is, again, away from the equilibrium line. Now, this isn't the way that Mother Nature likes to roll. So once we have this kind of disturbance, Mother Nature wants to go back to equilibrium, all right? So we can figure out the new concentrations and stuff like that from there. They had an example of a Q in there. Remember that Q and K have the same form, products over reactants. If you found Q right here, it would be products, 1.25, divided by total reactants, which in this case is 2. That number is going to be less than 2.5. So you're not at equilibrium. You can make predictions how things are going to go. But if nothing else, butane is the reactant, isobutane is the product. We add a lot of reactant. Is this reaction going to shift to the product side or shift to the reactant side? Product side, all right? So Le Chatelier's principle is awesome for making predictions as to what's happening. You can go math crazy on this kind of stuff, trust me. But if sometimes to make sure that your numbers make sense, you can back it up to things like Le Chatelier's principle and the value of K to make sure that your answers are actually okay. So what scientists would do in this kind of case is once you add the extra butane, the 1.50 extra, you can quickly do a Q calculation just to see if it's going to stay there. And we wouldn't predict that, but let's make sure. So Q is just like K, products over reactants. The iso is still 1.25 at this point, and the butane is a total of 2. And this number is much less than K. So Q is less than K. This reaction is not at equilibrium. And if Q is less than K, it first of all tells you that the reaction is going to shift. All right. We expect that this reaction is going to shift to the product side. We need to make this number look more like this number. It needs to get bigger. And the only ways mathematically you can do that is to make the top number bigger and or the bottom number's smaller. And both of those mean more product and less reactant. So what you can do is you can set up a type of an ice table to see what the new equilibrium constants are. The total butane here is 2.0, 1.25. Q is less than K. More product means we're going to have a positive X by the iso. Less reactant means minus X for there. So at equilibrium, 1.25 plus X and 2 minus X are going to be the values we're going to plug in. So once you have these numbers, we'll set them equal to the K of 2.5. I don't have it on there, sorry about that. We'll set those numbers equal to the 2.50 number. So how you want to solve for X here, you would first multiply both sides by 2 minus X. So you'd have 2.50 times quantity, 2 minus X. You would then combine the values to get X of 1.07. If you have nothing else to do this weekend, and don't throw tomatoes at me, this would be a cool thing to practice to make sure that your algebra is up to speed, and if it's not, boy, you let me know. At this point then, if X is 1.07, then the butane will be 2 minus that number, 0.93. The isobutane, 1.25 plus this number to get 2.32. Equilibrium has shifted to the isobutane. All right, we'll start with this example on Monday, so we'll do it again. Have a wonderful weekend. I'll see you guys on Monday.